Okay, let's start. The next minutes I will talk about serverless testing and why it may be a little bit more complicated than it seems to be. I work for a company from Germany called Open Knowledge. We work in whole Europe, especially in enterprise computing business, cloud, microservices, and also serverless. That's something about me. So let's ask ourselves, what is the big question about testing serverless, or the big issue about testing serverless? Because the serverless function is very small, and so testing shouldn't be too complicated. Famous last words. And if we take a look what testing means, testing normally means gaining confidence about your code running as expected in a special target platform, in this case, cloud platform. And testing is about minimizing risk that something unexpected will happen. And the question is, what does this mean, gaining confidence and minimizing risk for a serverless world? And because we are on a serverless conference, I'm quite sure everybody knows what serverless means. It means run code, not servers. Or as Amazon would say, run your business code highly available in the cloud in response to events and scale without any servers to manage. This sounds very promising, but when you're a little bit familiar with distributed systems, for me personally, it sounds more like a threat than a promise. It sounds like running your business code in a highly distributed, event-driven environment, or non-transparent environment, with no single point of control. So we live in a world like this when it comes to serverless. And testing in serverless world means gaining confidence in a world like this, in an environment like this, and minimizing risk in an environment like this. I have a kind of showcase that I want to show you right now, a special use case. And with the help of the use case, we want to deep dive into how to test a situation like this. And the showcase is an image gallery, and the use case is a very simple use case, uploading an image. So what does uploading an image mean in a serverless world? Normally, you have a user that the user, he or she, uploads an image, and normally you have a kind of API gateway in the middle of the processing. So the user does not call the serverless functions directly, but with the help of an API gateway. And the API gateway has several tasks to do, for example, some parameter mappings, header mappings, and also translating, in our example, translating the JSON HTTP-based or the HTTP-based JSON request to an event trigger for the Lambda function. Then we have the Lambda function itself that is triggered by the event, and the Lambda function in our case should store the image inside cloud storage system, which is in the AWS world, the S3 storage system. In addition, we want to store several metadata of the image, for example, weather condition while taking the image, or the location of the image, like it's an image from London. So we have a second Lambda function running, or be triggered by the API gateway, that stores this metadata. And of course, we want to do this in a kind of transactional way, because we do not want metadata in our database without having the image in the storage system. And on the opposite side around, we don't want to have the image stored in the system without metadata. So we need a transactional boundary. Also, what we want to do is to generate in the background asynchronously a thumbnail of our image. That's the third Lambda function, generating a thumbnail and putting the thumbnail in a special place, thumbnail bucket. And we also want to inform subscribers of our image gallery that a new image is available for example, a special location like London. So what we have right now for only uploading an image is a world of at least 4 Lambda functions, a lot of cloud components that are involved, and several asynchronously events running around. And that is a world that we have to test to gain confidence. But that's not all. We need, of course, something like user management, authentication, authorization. We need permission management. We have something like under the hood involved cloud components. In this case, it's CloudWatch, that is the distributed logging system of AWS, and something, for example, like routing to manage different stages of our cloud-based application, like a production stage and integration stage. And so depending on the route we are coming to the gateway, we go to the first or to the second stage. And then we have several components more. And so the question is, what do we have to test? What can go wrong? And everything that can go wrong, we have to test to make sure that the world is running as expected and to gain the confidence I talked before. And for our simple example, it's not only about the serverless function or the serverless functions, in our case 4 function itself, but also about the playing together, the integration of this function. So what can go wrong in our scenario? First of all, of course, the user can send, can make a wrong call to the API gateway. For example, not allowed HTTP method, or wrong payload, or wrong header information. And we have to make sure that this does not happen. The second thing that can go wrong is obviously we have to guarantee that the business logic is doing what it's expected to do, and we have to make sure that we have no coding errors. Because we live in a kind of we have a kind of transactional situation with this image storage and metadata storage, we also have to assure that this transactional behavior runs as expected, and we also have some asynchronous triggered events in the background, like this notification stuff for customers or the thumbnail generation, and we have to make sure that the events, for example, will not get lost, that we can handle double send, resended events, and so on. We have to make sure that that letter queues works as expected, and lots of more. And also what we have to ensure is that the chaining of serverless functions will not result in unexpected behavior. Maybe each function itself behaves as expected, and each function itself does not run in a timeout, but if I couple several of them in a row, which is very common, first we call one Lambda, then it sends an event, this triggers another Lambda, and so on, and the last one sends a result. The coupling or the chaining of the event of the Lambdas could run into or bring us into problems. And we also have to make sure that this will not happen. Then, of course, we can run into security issues, routing issues, and let me take a little look. And also API gateway related issues that in the gateway we can, for example, define route stages, versioning, and so on. Mapping of payload, mapping of header information, and we have to make sure that this runs. And of course, we live in the cloud. And the cloud is kind of fragile, so we have to be careful about outages of the cloud and use, for example, account limits. We have several account limits, and we have to make sure that we do not exceed these account limits, and lots of other things. Okay, this is a kind of summary of what I have said before. So we have to take care about internal programming, business logic errors, abnormalities, which means unexpected or invalid calls, lost or duplicated events, latency, timeout, and so on. So run code, not servers, seems to be kind of complicated. And the question is, again, as a reminder, what do we have to do to gain confidence in our code, in our highly distributed world, in this event-triggered, highly distributed world? And how can we minimize risk of failures in production? And I guess you all know the test pyramid, as I wrote it or painted it down here, which where you normally write a lot of unit tests to make sure that your business logic is running as expected, then some integration test for services running together or working together, and then only a few automated or a few end-to-end tests, because that's kind of expensive. And maybe you have some users that click around, or automation for clicking around and testing the UI. In the serverless world, it's a little bit different, because the biggest complexity in the serverless world is not in the function itself. The function itself should be normally very small, and the main behavior of a function itself is gluing other cloud components together. So just, for example, triggering database storage or a storage system or an event queue or something like this. So the question is more about how the function interacts with other functions and other cloud components. And that is where we have to minimize the risk. And when it comes to minimize the risk, we have several groups, or we can group the risk we saw before. We have something like configuration risk, which means our databases and database tables are set up correctly and configured correctly. Do I have the corresponding rights to permissions to access my cloud infrastructure? Then we have something like technical workflow, which means am I parsing the incoming request in the right way and stuff like this. We have business logic, which should be very small. And then we have a lot of integrational stuff. It means working, or the cloud components working together. So the highest risk is in this integration area. And this is why the test pyramid in our serverless world looks more like a honeycomb. So the main focus should be on integration and not on unit testing or end-to-end testing. For the next minute, I will take a short look on the different layers. What are the main purpose of the layer? And then we will do a more deep dive into each layer. And I will explain to you what are the main or the best practices to test inside these layers, like unit testing and integration testing and so on. So let's start with unit testing. And unit testing is for the serverless function itself. So what we want to do here is gain confidence or make sure that our business logic is working as expected. And as I said before, this means making sure that we have no business logic errors and no coding errors. That's all. The problem about this is, especially in the cloud world, that we have a lot of infrastructure, cloud infrastructure code inside our serverless functions. For example, accessing DynamoDB via DynamoDB AVS client, or storing something in the S3 storage system, so we have to get a client and store it with the special methods of the AWS infrastructure. So it's very important, or best practice, to separate our business logic from this infrastructure code. And of course, we can mock dependencies to this infrastructure code. We will see this in a demo later on. And therefore, we have frameworks like JUnit, TestNG, and Mockito to do this test, or this is a Java world, and Jasmine, Mocha.js, Jest, and different others in the JavaScript world. So this is kind of easy if we reach the goal that we separate the business logic from the infrastructure structure logic. When it comes to integration testing, it's about the cloud component and their interaction. So we want to make sure that the interaction of our serverless function or functions with all the other cloud components works as expected. And this is something like we want to make sure that we have the right DynamoDB query, that we work with the expected response and request format and so on. So it's all about integration. And the problem with this layer or with this kind of testing is that we normally need these cloud components to test their integrations. And this means we can deploy all the stuff, all the serverless, all our serverless application in the real cloud world, or we have to normally to deploy it in the real world, in the real cloud world, to be able to test the functionality or the integration. But this, of course, may become kind of expensive if for every integration test, every developer deploys everything in the real cloud. And so another solution could be to work with mock or fake cloud components, like S3 server, which is a mock component, or DynamoDB local, which is a local version of the DynamoDB database. These are all, by the way, these are all examples from the AWS world, but of course we have nearly the same for all the other cloud worlds, like Node Lambda, fake SNS, and so on. So we need mock components, or can use mock components. The problem with mock components is not local components like DynamoDB, but mock components is that you tell them how to behave. And if you tell them how to behave, normally they behave like you tell them they should behave. So they will not run into the same problems like the real environment. So self-fulfilling prophecy. Last but not least, end-to-end testing for user stories. So make sure that chains of serverless functions and cloud components work as expected. And here we talk about things like wrong permissions. We talk about timeouts that are not set correctly. We talk about memory allocation. We talk about exceeding an account limit. And we also have to test this. And this is very hard to test if you don't go to the real cloud. But even here, we have several possibilities to first test it local and then go to the real cloud to save some money, like in the AWS world, SAM local, local stack, or serverless offline, which are some frameworks. I will show one of them later on. Okay, so this was the basic, but what are the best practice to do testing in a serverless world? Right now we have this Rowekamp thing, so it's mostly about integration, but we still have to do some unit testing, and I said we have to separate logic from infrastructure and so on. So let's take a deeper look into this. And I have brought with me several best practices, and the first best practice is to separate business logic from infrastructure code inside your function. And what we see on the next slide is on the left side, you see the on-premise world, so what you have on your local computer. And on the right side, you see the cloud world, so what you have deployed in the real cloud. And in the middle, we see our Lambda function we want to test. And the first thing I said is, if you want to do unit testing, you have to separate your business logic from your infrastructure code. And if we take a look at the code, I hope it's readable, then we see something like this is a AWS handler methods of a AWS Lambda, and it's a very, very simple hello world that should return a greeting. And what we see is that we have a mixture of infrastructure code and business logic. The business logic, okay, we cannot see it here. The business logic is this if statement. If first name not equals last, if first name and last name not null, blah, 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 means greeting response, create a greeting response with the thing that comes in and then send this greeting response out. So this is a business logic, but we have a lot of infrastructure logic around, like this Lambda logger, get the Lambda logger, which is a special logger who's not familiar with AWS, a special logger for the cloud environment, so you cannot run this on your local machine. And we have a context object in the signature of the handle request message. So this is infrastructure. And the first thing I said before is to separate this. So what we can do is we can put our business logic in a special class like greeting service and keep the infrastructure code and the call of this business logic inside the handler. And so it's very easy to test the business logic without any infrastructure code just by testing this greeting service, as we see here. This is a test case, JUnit test case, and what we do is we call our greeting service with our input parameters and ask for a special response, and normally this should be green. And we see no AWS Lambda-specific infrastructure code here. So the second best practice is to mock your infrastructure code for unit testing. Because even if we get, if we separate our code as shown before, we also want to make sure that calling the handler, the AWS handler, with a correct response leads to correct request leads to a correct response. And if we call it with an incorrect request, it should lead to an incorrect response. So we have to test also the handler method, not only the business logic. And the problem about this is that, again, we have this infrastructure components like the AWS context and the Lambda logger, which is not available on our local machine. There's no library for this that we can use locally. And what we can do is, first, we can get rid of some of these infrastructure components by using cloud-agnostic infrastructure. For example, the logger, we can get rid of the logger by using a cloud-agnostic logger like Log4j or something like this. This is very easy to get rid of this, and we can use this logger in the cloud and also on our local machine. So it still works in the cloud. That's very important. And of course, we can also use interfaces. And one implementation could be the real cloud implementation, and another implementation could be our special implementation for testing. But this is a huge effort to manage this. And to not to have to do this, you normally, and this is a second solution, you normally fake or mock these cloud infrastructure component. And this is a test, again a test, and what we did here, or what I did here is I faked the context, the AWS context of the Lambda function by just writing my own context, which is called test context. And what we see here, class under test handle request, this is calling the Lambda function. And I call this with the original request and the context is not the AWS Lambda context, but my fake context. And the only thing I have to make sure is that it behaves, when it's called inside my Lambda function, that it behaves like the real context. This also means a lot of effort if there's a high usage of this context. So as I said before, I have to make sure that it behaves like the real one, and so I have to program or reprogram the context, the real context. What I else can do is just using a mocking framework like here. We see, I know what, in this case, I know which functions of the context will be called during this Lambda handling, and so I just use a mock framework and say, if this function will be called, then return something to make sure that it works. Okay. What we did right now is just unit testing something and make sure that our business logic is running as expected and the handler itself is running as expected if we fake or mock a context. But what we also can do is span up the whole, not the whole, but parts of the cloud environment locally and run the real Lambda function locally. So our real deployment artifact that we normally would deploy in the cloud, we are able to run this locally. And We can do this with the help of a framework called SAM. SAM means Serverless Application Model. And the serverless application model helps us to declare our function and the needed infrastructure and to deploy it. And this is what we want to do right now. So we have a kind of description of our method and the infrastructure our method needs, like we see over here. We have our greeting function, and what we see over here is that our greeting function, the handler method, is de open knowledge something greeting handler, that you can find the greeting handler in testing 1.0 snapshot jar, and you see runtime is Java 8, and you see also several information for the API gateway. And with the help of this description, we can deploy our Lambda function locally with this call SAM local, or we can invoke our Lambda function locally with SAM local invoke. I go back once. You see also third line greeting. This is the name of the function. So every function, you give a name to every function, and this is a name. And what you see here is that it's very easy to call this function by name, SAM local invoke greetings, and then, of course, we need the event that normally is triggered by the or sent by the API gateway, and we can give this via parameter. So this event greeting JSON means there's a JSON file in my file system, and I use this to trigger the event. And that's the result. On my local machine, Docker container started with an AWS fake environment, and the Lambda function is running. So we can use this to test the call of the Lambda function locally. So next, the problem about this is that normally you do not call the function directly, but via API gateway. And as I said before, the API gateway, or via another component, it's triggered via, for example, the storage system or the DynamoDB or something. And the resulting event, so when calling the API gateway from the user side, the API gateway will enrich your call with additional information and will change the structure a little bit. So what we have to test is not that JSON structure that the user will send to the AWS function, but what the gateway will send. And there is also an easy way to do this with a SAM description, because we can start the gateway. We can say SAM local start API, which means span off the gateway on port, in my case, 8080. And then this gateway is waiting for a call, and we can do a call like the real user is doing, and all this mapping and stuff that's going on in the API gateway will take part locally on my computer via SAM local. So I just send this request to the API gateway, port 8080, and everything else is running automatically. And this is the result. And just for your information, this is the transformed payload of the gateway. So when I send only first name and last name as payload from the outside, from the user side, the gateway transforms it to payload like this. Okay, so next, I think 3 more to come. Next, best practice, use local cloud components for basic integration testing. And I will run a little bit faster over this. This means just you can install DynamoDB locally or the S3 locally or stuff like this locally. And what we want to test is that our Lambda function called this local DB, for example, or local storage system, and that these components triggers our Lambda functions. For example, if I put something, if I put an image in this S3 system locally, I want an event to be triggered or event to trigger our Lambda function. And of course we can do this, but it's very important to understand that these local cloud components can only prove functional correctness, but not infrastructural correctness, like dead letter queue behavior, like timeout, like throttling, and stuff like this. They do not behave like the real world. They behave in a functional way like the real world, but not in the infrastructural way. Okay, first I will show you how to generate, with the help of SAM local, how to generate an event. For example, I simulate that I put something in my S3 bucket, or that I put data in my DynamoDB, and you only have to say SAM local generate event with the service like S3 and the option like put, and the result will be an event like this. And now you can use this event and trigger your Lambda function with this event. The other side around is to install your cloud component locally and call it locally. And in this example, we see how to start DynamoDB locally. And now we can define an endpoint like 80,000 in my case, and just call this DynamoDB like the real cloud component. And what we can do is, for our DynamoDB client in our AWS Lambda code, we can configure it that it works with this instance instead of the cloud instance. And so we can do integration testing with database, storage, and so on locally. Okay. So 2 more very fast things to come, or best practices to come. The first one is use temporary integration cloud for partial integration testing. As I said before, we are not able to simulate the real cloud world inside our local environment. And there for sure comes the time when you have to span off parts of your application to test the integration in the real cloud. And what you can do is you can also use SAM, the same SAM description, same SAM YAML we had before, to span off the whole world, or not the whole world, but these components you need for your integration test inside the cloud. That's very easy. So the same way I deployed in my local machine, I can deploy it in the test environment just for several seconds or minutes to do the test, and then tear down everything. So I only have to pay for the moments I test and only for the components I test. This works very well, and this is a very common best practice. And in addition, you need something like a permanent integration platform inside the cloud where you simulate your whole application. This is something we normally do, and this is the only chance to get rid of all these problems like account limitations, like chaining of functions and running into timeout problems, and so on. And the only chance to debug the real-life behavior of your system. Okay. So, are we gone? We talked about unit testing, we talked about integration testing, and we talked about end-to-end testing. Are we done right now? And I have this quote from Charity Majors, and she said something like, testing don't end when shit is deployed. And that's right, because as I said before, we want to gain confidence about our code. And of course, we live in a very fragile environment when we live in the cloud, and we have to take care about, for example, cloud outages or outage of components. And you may say, okay, when working with Azure or AWS or Google, there is no outage. But when you think this, you're wrong. We have a lot of examples when at least parts of the cloud was not available, and we have to handle this. What we also have to do is to set up a robust monitoring and error reporting, like logging, tracing, metrics, alerting, to anticipate disruptions and to be able to automatically recover before something really explodes. And last but not least, we have the chance to inject small doses of failure into our system via cars engineering. Okay. So just keep in mind, or take home, testing does not end in production. So that was my talk about testing or surviving testing in the serverless world. I hope you understood that it's not enough just to test your simple serverless function, and that it's not enough just to test the integration of your function with some of these cloud components locally, but you have also to span up at least part of your environment in the cloud, and for real production testing, you also have to have a very production near environment in the cloud. Okay, thanks a lot.